Friday. We made it to Friday. Do a little bit more and start the weekend. Homework 6 is posted for the class. It has some book problems and a little bit of computing to look at, apply some confidence intervals to data, and do this procedure called a bootstrap with a standard error. And so the goal today is to understand better how to make confidence intervals for a population mean, how to understand the formulas, see what affects the formulas, and then how to get at the standard error of X bar through a simulation technique. There you go. Oh, I put one already on your, over there. You have one of those ones. You don't need to. So the scenario is that we're interested in is that we have a population out here, and we're interested in the population average. That's what we really would like to know, and that's given this Greek letter mu. Okay. And we're going to take a sample from that population and record a bunch of measurements, x1, x2, xn. And that's our data that we're going to record. And we're going to take the average of those, right? Just record a sample average. And that's our estimate of mu. Mu is this value of X bar. But we don't expect to hit it exactly. And to reflect the uncertainty in that, we're going to put a confidence interval about it. The standard error of X bar, we're going to talk about what that is. And then we're going to use that to make a confidence interval for the population mean. And the CI is my abbreviation for confidence interval. Let's motivate this with an example. We're going to look at some outcomes today related to the pregnancy. And so the first example looks at length of pregnancy. We can think about this as being for women who are singleton births, without major complications. So that whenever you're collecting data or summarizing something, it's relative to some population that you can define. Right, hard to see. Right, over here. So let's say we have 60 women in our sample, and the average days of gestation before live birth, is 266 days, and that the length of pregnancy has a standard deviation, we'll call sigma, of 16 days. Now, would the length of pregnancy really be normally distributed? Think about it. You go up, you get to 37 weeks, 37 and a half, 38, so, there's not many pregnancies that go much past 40, 41, 42. But there's a number of infants and babies that survive at younger ages. So the distribution of length of pregnancy in days is probably kind of skewed, right? A little bit skewed. Left. So that we wouldn't model just with a normal distribution, say, because it's kind of skewed. The distribution of X bar, however, based on 60, should be really quite symmetric, the distribution of X bar. And it's symmetric about the mean, whatever that is, what we want to know. But it should be much more normal. X bar should be approximately normally distributed in different samples. Right across samples of size n. So this says that X bar is approximately normally distributed. I forgot to write normal. Right, let's put in there. approximately normally distributed across samples of a certain size. Right? So the average values, you get one sample, you get one value, you get another sample, 60, you get another one. If you look at all the averages across those should roughly follow normal distribution, even though the length of any individual, if you took just individual values, they wouldn't look normal because of that thing, right? And the distribution of X bar, the spread out here is described by the standard error. Right? So if we draw a picture here that says here's the distribution of X bar, here's mu, that kind of around the mean, going up about 2 standard errors, going down a couple standard errors, right, where the standard error is the standard deviation of X bars in repeated sampling, kind of the spread of those X bars. Right? About 95% of the time, we're going to be plus or minus about two standard errors. Right? Right. So if we can figure out what that standard error is, we'd have a good idea of how accurate our X bar would be. Right? So the standard error, standard deviation of our X bars, if these are independent samples, is like the standard deviation of one individual divided by the square root of the sample size. And this is called the standard error. So in this case, sigma was 16 days, and our sample was, we say, 60 women. So the standard error is this 16 over the square root of 60 is 2.066 days. So our estimation is going to be twice that is about 4 days. So plus or minus 4 days is kind of the accuracy, which we're going to get some estimate there. Right? We're not actually going to use 2 exactly for this. We're going to look at the standard normal to figure out a different value. The standard normal value is going to be about 1.96. It seems like a small change, but it's just kind of the exact value from this distribution. And so let's think about where that is. We want our intervals to cover the truth with a pretty high percentage. So a 95% confidence interval is going to look at how many standard errors do we have to be away from the mean to cover 95% of a normal distribution. So everything is relative to standard errors. If we look at a standard normal, the normal 0, 1, random variable, and we want some symmetric interval in here that has 95% of the area. And we need to look up that z-value that will cut off 95% when you do plus or minus. Well, if there's 95%, right, there's 5% out in those tails, and that's symmetric. So it's half of that is 0.025. So this point up to here, right, is not the 95th percentile, but you have to take this first 2.5% and then this 95 and add them together. So the point we're looking for is the 97.5th percentile. Or in the Rosner's table, we had X and A of X, the columns. We're looking for the point over here that has about 9750, right, as the area, right? Because his curve A would take a point here and then give all the area, right, going back. This area in here is A of X. And the value that matches up to that is 1.96. So the 97.5th percentile is 1.96, and because of symmetry, the point that would cut off and equal 2.5% tail down here is negative 1.96. So our confidence interval, we're going to take our x bar and add 1.96 standard errors to it and subtract 1.96 standard errors. And that should cover about 96% of the, what we're going to call that confidence. We'll kind of talk a little bit about what that means. You can think about kind of 95% of the chance in some sense. So our interval, 95% confidence interval for mu, in this case, the average length of pregnancy, is formed by taking x bar minus the normal value times the standard error. I like to write this in a couple ways so that you see where things are coming from. And in this case, it's x bar for 95%. That's where we get the 1.96 value. So 1.96. And dealing with x bar, the standard error we're going to use right now is sigma over the square root of n up to x bar plus 1.96 sigma over the square root of n. And that's going to be our 95% confidence interval where we think the population average is. All right. So if this was 266, if this was 16 over the square root of 60, because we have 60 women, and that went up to 266 plus 1.96, 16 over the square root of 60 is going to be our interval. And multiplying those together, 266. This thing multiplied together is about 4.05 up to 266 plus 4.05. So we're going to get an interval that goes 270.05 down to 261.95, and that's in days. So if we had 60 women and they had an average of 266, and the other assumptions about deviation were, for this population represent these women are a sample from, the average gestational age at birth looks to be between 262 to 270 days. And then so we report with confidence that it seems to be like, in that interval. What happens if, yes?
Where did the 1.96 come from?
The 1.96 is going to be the z value, right?
Okay.
Coming from that normal.
Okay.
Right, so in the normal area, under standard normal, from that curve is going to get the 1.96 cutoff.
Gotcha.
Now we can change the level of confidence. We can be more confident of covering the guy. We can make it 99%, so we're going to have to make it wider. Or you can do 90%, which would be a little narrower, but we'll go through a variation like that. So that's tied to the normal. And so it's really a property of the procedure that we make these intervals, and we want 95% of them to cover. Right? And so we set the width, the multiplier there at 1.96 because that's what's appropriate for normal 95%. All right, so variation one, right? The group of women that we're studying is more homogeneous than before, and now the standard deviation is only 8 days. Why would it be more homogeneous? Maybe these women are in a certain age range, maybe they come from a certain part of the country, might be more homogeneous in terms of other risk factors, maybe they don't smoke, maybe they don't do drugs, or maybe they're not really young, really old, or something like that. Or maybe they haven't had complications before, no history of preterm birth. So it's more homogeneous, it's less spread for them. Well, we get 60 women, and the average is 266, and I want to do a 95% confidence interval, right, for the population average. Of this population. So 95% is, right, Z is going to be 1.96. Right? Now what's the standard error of X bar? Well, sigma over the square root of n. So the standard deviation was 16 before, right? We're half as much. Right? Directly translates into smaller. And it's 1.0. That's also in days. So our confidence interval has the same form, X bar. So instead of writing minus and then plus in two parts, right, I'll put plus or minus a Z value times the standard error. X bar plus or minus a Z value. In this case, it's sigma over the square root of n. And so 266 plus or minus the 1.96 value times, well, we can just do that comes out to 1.3033, plugging in those numbers. So our interval is 266 plus or minus twice that, so about 2.02. So our interval, you add 2 is 268.02, you subtract, that's 263.98 days. So that would be the new interval, if in fact our sigma were smaller, as more homogeneous. That'd be better, right? That'd be nicer because it's smaller and it kind of reflects the spread of the population. What would happen if it was a more heterogeneous group? You have more mothers, there's more, got a visitor looking in the window out there, I guess, a squirrel. Anyway, but it's outside. Ah, it's really looking at If it was more heterogeneous, and you had a bigger mix of women from different types, right? You had a more mix of, maybe you had some women from some areas where there was more drug use, or smoking, or more pregnancy among young women, and then another group that was, it is just more diverse, right? You could get or you expanded the inclusion criteria. So maybe you don't know if some of these women have had problems in the past, and they're also included in the study. You got a sigma that was like 24 instead of 16, right? Then it's going to get wider. Right? What if you had a bigger study? So instead of 60 women, say you had 540 women. But again, we're going to take the same average, assume go to that 16 standard deviation in terms of days, and we're going to keep it 95% confidence. So we're going to use our D of 1.96 from the normal. Right? How's this going to affect things? The standard error, is that going to get smaller or bigger? Smaller, right? Standard deviation is the variability of X bar. And if you're averaging more things together, that's more information, and it's less variable. This is the letter. And so the standard error of X bar is the sigma over the square root of n. So now we get 16 over the square root of 540. And it's about a third of what it was before. That's 9 times increasing. So it's about a third of what it was, and a third of what we had before, 0.6885, right? The standard error. 9 times as large. The confidence interval, because that's smaller, everything else is equal, 95%. So we're going to get X bar plus or minus our Z value times the standard error. So 266 plus or minus 1.96 times that standard error. So 266 plus or minus 1.35. And now our interval is more precise, 267.35, 264.65 days. So if we had 540 women, it would become a lot more precise. You could, there's a lot less uncertainty, so Still, 266 is right in the middle, that's our estimate, but this expresses the uncertainty relative to the sample size. This term over here, right, those two together is usually referred to as the margin of error. The z-value times the standard error, kind of half width of the confidence interval. Any question? What happens if we want to go up to 99%? We want to make a confidence interval that has 99% coverage. Well, that 99% came from a normal distribution, a z distribution, normal 0, 1. That's centered at 0. Now we want to pick cutoff values, z-values, that get us 99%. So this is going to be a little bit further out here. So you might try to draw it so it looks a little bit further out. What percentile do I have to look up in the table to find the cutoff value?
0.995.
99.5, yeah. So there's a 0.005 out here and a 0.005 out here. That's half of my 1%. Right? And so all the way up to here has to be 99.5 percentile. Yeah, that further value out there. It's going to be bigger. It's around 2.57, between 2.57 and 2.58, and so kind of a value that's usually used is something like 2.57. If you looked it up on the computer, it would be about that cutoff value. It's wider than 1.96. 1.96 back here. It's a little bit further out. It covers more of the area. So our 99% confidence interval for mu, for the population, right? We always do confidence intervals for the population, for the parameter, the thing that we don't know. Right? When we center it, we base it on the sample, because we know that. X bar plus or minus the z-value times the standard error. In this case, for 99%, it's 2.576 instead of that. We have before, so 266 plus or minus 2.576, and this one is 16 over the square root of 60, and going back to the original conditions. And so that's going to be like 266 plus or minus 5.32. So it's wider than the original because we want bigger confidence. So there's a standard phrase that we're going to use to describe confidence intervals. So 99% confidence interval, we'll get this interval. Right? And we're going to say we're 99%, or 95% if I'm talking about that, 95% confident that my interval covers the real value of the parameter. Right? The truth is out there somewhere. Right? It's some value, some average, 267, 268, something like that. Right? It's really out there. We're going to get an average based on a random sample and plug down this interval. And some of these intervals will be in the right place, as we do this over time in different applications. So we do this every year from a new sample, and some of them will miss. So we're going to have some population average out here. And if we get one sample, we're going to plug down our X bar, and we put an interval about it, right? Something like that. And some of these will be situated such that the interval actually covers the truth. Sometimes if we do this again, or the next year, right, we're going to get a new X bar and a new interval, and it might cover right, in any number of things here. A lot of them are kind of probably pretty close, right? But every once in a while you get an X bar that's a little further away, and it misses on that side, or maybe this side. It doesn't quite go all the way, and some of them miss. Right? The idea of 95% confident is that we get about 95 out of 100 that would be of this type that would cover the truth and be the X bar would be close enough that once you put the margin of error on it, it's wide enough to cover. But some miss, 5 out of 100 are going to miss, either high or low, depending on things, just by chance. Every once in a while you get an extreme result, you get an unusual sample. It's going to happen in your lifetime that you're going to get that, and so some are going to miss. Right? If you have pretty big sample sizes, even if it misses, it's probably not going to miss by a whole lot, but it still misses. Right? The idea of 99% is we want 99 out of 100 to cover. Right? So how does the picture change if we go to 99%? 99%. 99 out of 100 to be covering, and just 1 out of 100 miss. So going from that 1.96 up to 2.576, right, makes it a little wider. So the 99% is like adding a little extra length onto all of these intervals. So the ones that covered before are still covered, and some of them will still miss. But there's these few, there's 4% that it missed when it was 95, but it gets a little bit wider and it covers. So in confidence intervals, we really want two things. We want nice narrow intervals. We want them to be really precise, because you want to be able to say very precisely, where is it? Where is the mean? But at the same time, a 50% interval or 40% interval that would miss most of the time, it just doesn't seem very good. Right? So the kind of consensus is something like 95% intervals are very typical. Could use 99 for some things. Some government agencies use 90%. I'm not sure they understand what they're doing, but in any case, they do. But 95% is pretty typical. Right? So just as an example of intervals, I uploaded to the website is an article. It's medical. The Cochrane Library is an organization that does, they call systematic reviews of medical literature. So they'll take an area of medicine and then find all the studies they can in the US and internationally on that subject. Find the ones that are randomized controlled trials where they clearly define how they recruited subjects, how they enrolled them, do they have written consent and other things like that, and take the results and then combine them together. And that's called a meta-analysis, to bring things together. So this one is on so children with this HIE, this hypoxic ischemic encephalopathy, have oxygen deprivation during birth. And so after birth, they're having some brain problems with brain. And so this can lead to death, can lead to cerebral palsy, blindness, and many other things. So it's a very serious condition. And so one idea that was developed over the last 20 or 30 years is that if you keep the body temperature lower, so there's less cellular activity, there'll be less deterioration. So it's a treatment that if the baby's born and there's signs of relevant problems, that you can do a whole body cooling. You can cool the body down a few degrees. It slows the process, and it seems that the processes, the biological processes that lead to brain damage were slowed. So after this period of time, when you warm the baby back up, it has a better case. And so there's all these different studies of this, randomized controlled trials of this. And so page 61 of this thing about there starts to show, there's a lot of discussion of the different studies, how they define things and things. But this is a summary of the different analyses that they did. Right? And so the first outcome is death or major disability in survivors. Right? And so the individuals were cooled, or the randomization was not cooled, standard therapy. 8 studies, 1,300 individuals there. And they're not reporting averages, they're reporting something called a risk ratio. But the thing the key summary is this 95% confidence interval. So here's the estimate of 0.75 as a risk ratio, and then an interval. And in this case, a risk ratio below 1 means that cooling decreases the bad outcomes. So 0.75 is below 1, so cooling is good and should be done. And the confidence interval shows you, well, how far is it below? Are we sure it's below 1? Are we sure it's really been? Yeah, so this is all clearly below. Even if this had been off a little bit from the truth, it's still way below 1. Right? I think there was a couple ways of whole body cooling or head cooling. Both of those showed the same benefit. Mortality, just major neurological disabilities, and then they go through a whole series of different outcomes. Some of them are significantly different than 1, they're smaller. Some of them are not. If it goes above 1, or this one, it's like it's very wide. Right? There's different scales. There's a mean difference, kind of an average difference, so that's a different scale, so it looks very different. But in this case, it would be relative to 0. So anyway, the confidence intervals get used as a 95% confidence about the key summary. A few pages later, they kind of go through looking at, this is review, cooling, death or major disability. There's 3 studies that had selective head cooling with mild systematic hypothermia, right? And then there was some other studies that had whole body cooling, and then they put them together. So they were called confidence intervals for all these things, right? And the clear message out of all of these things is that it's overwhelmingly effective, right? So they didn't look just at one outcome, but the confidence interval was a major thing to show that it's just not random chance that it's better. So anyway, I found that interesting, that how much they rely on confidence intervals. And so, although the different formulas for different standard errors, different statistics, it's the basic same structure for data protection. So anyway, that's there. In case you're looking at that as a real example of this, right? But any questions about the confidence intervals? Let's do a little bit of outline of how the book covers some of these things. Right? Because there's going forward, we're going to try to keep track of this, and because in each chapter there might be a couple ways of doing confidence intervals and different things, and so the number of possibilities expands quite a lot. The book is very good at laying out a lot of possibilities, but we're going to focus on a few key ones for studying to get the main ideas, right? So in this chapter 6.5, talking about what are estimators, functions of estimating, it gives you that the standard error of x bar should be used as sigma over square root of n as a formula. Right? This is also called, this is also a standard deviation of x bar in terms of like probability. The special name we give it is called standard error, but it's really the standard deviation under a sampling distribution, hence the connection to the probability. The signal limit theorem, right, says that x bar should be approximately normally distributed. And so anyway, this normal was why we were using, say for 95%, we were using the z as 1.96 because that's the plus or minus 1.96 cuts off 95%. A formula for a confidence interval that we've just done is equation 6.7. That's the one we're using today. We're going to relax that. The equation, we're going to 6.6. We'll look at this one. It uses something called a t-distribution. And we'll do that. That's the plan for that one is on Monday. The idea of this other one, the t-distribution, is that we really don't know the standard deviation. Right? We really do estimate it from the data. Because you estimate it from the data, there's a little bit extra variability, so we kind of tweak the system. We tweak the interval a little bit to make it 95%, so it still covers 95%. So there's a little variation, but still there's going to be an estimate plus or minus a distribution value. We've used z so far times the standard error. It's going to look the same, but we're going to change a few details to make it more like it's really done in practice. We're going to skip, right, so also upcoming, something we will do, we will look at 6.8, which is inference for a proportion. For proportion in a binomial experiment. We're going to do that one too. So we'll have this formula, a formula for the t, and then a formula for inference for proportion. Right? We'll skip a couple sections. Not that they couldn't be done, but they just add more complexity to things. So we will plan to skip 6.7, estimation of a population variance. We're going to skip 6.9, which has got a Poisson random variable, Poisson rate. And 6.10 had one-sided confidence intervals. Sometimes one-sided confidence intervals are you can do, so we're just going to go from a lower end up to infinity, or an upper end down to negative infinity. So sometimes you're just interested in one side of a question. If you're trying to reduce blood pressure, you're not really interested in the upper side so much. You're more interested in the lower side. Or sometimes in drug comparisons, like there's already a standard drug out there, and you've created a generic, and they need to prove that it's at least as beneficial as that one. It's kind of a one-sided question. So sometimes one-sided get done. But that will, those other details. If you go on in statistics, medicine, biology, field biology, genetics, you'll learn a lot of details of different procedures for the data you're using. What we're stressing is this big idea that there's a statistic, there's a sampling distribution of it, and we can use, and that is the rationale for making an interval. And our intervals tell us things about where we think the population is. We're trying to emphasize those things. What we're going to do now to finish up today is actually in 611. And this is something called a bootstrap estimate of standard error. And the purpose of this thing is, of this other way of doing estimating standard error, is that in some cases, estimating is much more complex, right? And then getting a mathematical formula for the standard error is actually quite a challenge. In our case, we get sigma over square root of n. It works out just fine, right? But instead, sometimes we can use simulation to assess standard error. The other thing that by looking at this does, it emphasizes that the standard error is a characteristic of the sampling distribution. So let's take a look at what this thing says. So the key question is, how do we estimate standard error? So what is standard error? And how do we estimate it? So in terms of what is standard error, we begin with this scenario where we have a population. And there's some population characteristics, this three-letter view up here we'd like to know. So in practice, we get one sample. And we're going to have our values, x1, x2, x3, right up to xn. And based on those, we're going to calculate x bar. So what is the standard error of that? How much variability is in the distribution of x bar? So one way to get at that one, hypothetically, if we could have our population here, if we could take sample 1 and get x1, x2, etc., and get an x bar 1, reverse sample. If we could do the whole process again and get another sample size in, right, we could get a second sample and get an average for that one. Do it again, and get a third sample, and take another sample, and get another one. I'm going to put a capital B here for a large number of samples. Right? So if you could do it a bunch of times, you would get a distribution of x bars. And if the distribution of the x's was, some skew thing, right, kind of spread out, the distribution of the x bars is likely to be more symmetric and narrower. And so there's a difference between the data distribution and this x bar distribution. Right? The standard error of x bar is just the standard deviation of all those values from different samples that we would like to be able to take. So the standard error is the standard deviation of the x bars from many samples. So yeah, so if you made a histogram of those, you get some curve. And if you kind of estimated the variability here from a usual standard deviation, that would be what our standard error is, right? Express the uncertainty or the variability in our sample averages. We can't do that. We can't take multiple samples, right? So we need to do something that looks like taking multiple samples to get something that's going to be comparable. And that's what this bootstrap does. So we have our population with its population average. We take our one special sample, x1, x2, up to xn. And then the bootstrap procedure is going to draw new samples out of this one from the data we have, or in numbers, and allow a little bit of variability to get a new sample. So bootstrap. I'm just going to go back. Okay. Okay, so then we're going to do that again. Maybe I can get that. How would this go off? Okay. Bootstrap sample. 1. So we're going to get, in this case, you could call it x1 star, x2 star, xn star, a new sample. And we're going to take the average of those. And I'll call that x bar star 1. Like the average of the first bootstrap sample. We're going to pick these randomly from this. We're actually going to pick from this group with replacement, which means we're going to take our n values and pick one. And then we're going to go back to the full set again and pick again. Right? And we're going to do that n times. So we could get duplicates. Right? So this is with replacement sampling. But some of these original data might be left out, some might be duplicated. So it'll look like our original sample, but it'd be a little bit different. Kind of like getting another sample of data. Then we can do that again, right? Because once the data are in the computer, we can do this 10,000 times pretty quickly. So we're going to take a bootstrap sample 2. We're going to pick a first time, a second time, an nth time, and then take the average of those, and I'll call that x bar star 2. Now we're going to do that, a whole bunch of times. So bootstrap sample B, and we're going to get an x. We're going to get a new x1 star, x2 star, xn star. Sample from that group up there with replacement, so it allows some variability. I'll call that last one this. Right? And then let's call the average of all of those things kind of a double average, and average the averages. We'll start here because we're in bootstraps. The thing that we're going to do, the bootstrap estimate of standard error, is we're going to just take the standard deviation of these replicate values, these repeated x bars. All right, so we're going to take the x bar minus the star ones minus the overall average. We're going to square those things, add them all up, divide by the number of times that we do that, minus 1, and take the square root of that whole thing. Right? This, oops, I won't do that. Get this out of here. That thing is really the standard deviation of the x bar stars, right? And that is what we're going to use as a way of getting x standard error. Kind of mimics the process of taking multiple samples, right? But it's only from our data that we have. So actually this works. It's a real thing, yeah.
Is the p minus 1 included in the square root?
Yeah, I think it's, the square root would be under that, just like a standard deviation point. So we had n values, we did n minus 1. In this case, we have this capital B replicates. The standard deviation of those. And so this is actually the thing. The guy who described it first and did a lot of theoretical work to show that, yeah, this actually works. And gives you a valid estimate of standard error and other ways of getting confidence intervals. Is Brad Efrod, who's a professor at Stanford, who's been at Stanford since the 60s, but in kind of founded this area of statistics and simulation-based evaluation. Right? He got the first international prize in statistics from the International Statistical Institute, and he's been president of the American Statistical Association and a bunch of other stuff. Right? So. But it actually works to simulate. And I kind of like it because, you know, it makes this connection. Well, what is standard error? Well, it's the variability in the sampling distribution from taking multiple samples. Well, how can we evaluate that? Well, we can do this other thing that's kind of analogous to taking samples, taking bootstrap samples. And again, we'll take the standard deviation of those replicate values. And it's like getting a standard deviation of those other things. Right? And so that's a core understanding of what sampling distribution is in a way. Right? So let's look at doing this in R. We can do that with computing. Does everybody have a copy of the handout? So, do you need one? Maybe yeah. So for doing things on the homework, there's some R script and some data to download. So it would be a file. If you saved it, it would be one of these things. I give it the name of R script to make it clear what it is. It has that little R icon. I right-click on it and open it in RStudio, and then the R script opens up there. I think if you just double-click on it, it probably opens up in RStudio. If you see it with that little R icon there, it probably will go right into RStudio. And what you get with that is that it's up here, this R script. So we're going to imagine a scenario where we have 30 infants, and these infants have some risk factors associated with them in their birth. Heart rate monitors before birth, other characteristics look a little bit off, so they're at risk of things. One measure of breathing in infants is called the APGAR score. An individual, Virginia Apgar, described it in the 50s, kind of a way to quantify and codify how is an infant breathing at 1 month after 1 minute after birth. An APGAR 5 score is 5 minutes after birth, right? So if the baby's not breathing at 5 minutes, right? That's serious. If the breathing is labored or easy or intermittent, right, or not very deep, right? That's a measurement of some problems, right? So there's a standardized score for that, and you can look it up on a number of things here. So it goes from 1 to 10. I'm just going to simulate some data. So to simulate it, I'm going to set a random number seed. So I set this initial seed number to the random number generator so that if I do it again, I'll get the same result. It starts at the same place. Right? So I set that little seed. I'm going to generate 30 data points. I'm going to call them X. They happen to be just kind of simulated from a binomial, but it's really on a scale, I think, 1 to 10. And in my particular example, these are the data that I got. So the scores in my sample here, I can even show you the little, these are the score, APGAR scores for this group. 8, 9, 10 are much better. Right? So it's pretending that this is a group of infants that has some signal that there might be problems. Right? So yeah, this tabulation means here that there's a score of 4 occurred twice, 5 occurred 11 times, and so on. The average of these APGAR scores is 6.03. And the question then is, what is the standard error that I want to use for confidence interval? Yeah?
What does that set seed mean?
The set seed, so in the random number generator, right, it's generating random numbers, it actually goes through a little algorithm. And at the beginning of that is a starting point. Right? And if you set the starting point to be the same, and then go back and do it again, you get the same numbers. So if I generated, additional random numbers, if I do this, again, here, oops, copy it. copied. And I put it down here, and I do it, I get 30 numbers, because it was 30. If I do it again, I get another 30, and so on. But if I go back and set that random number seed, and then go through some of this random selection, so I did it once and oops, right? That's my original sequence. The second sequence here, this one, this 4, 5, 5, 5, 6, 4, matches the 4, 5, 5, 5, 6, 4, and I get the same thing. So if I wanted to, simulate something to prove something and give somebody a result, and I wanted them to be able to do the same thing, I could set the number seed, and then they should get the same result as I do. If you don't set it, it can be different every time because it's random. But you can control at least the starting point. So if I wanted you all to do the same, get the same homework answers, I could say set the random number seed and then do a random generation or something.
What's the 0.6? Is that like P?
So this would be P. In a binomial, this would be, 10 would be the number of trials and 0.6. I'm just using the binomial in this case just to generate data. And so I'm going to treat these data, the x that I actually have, these numbers as quantitative data. And so the mean of those, the mean APGAR score in this group is 6.03. So what's the standard error? Well, to take bootstrap samples, I'm going to do 1,000 times. And I'm going to set up a numerical thing to hold the averages, because I need x bar 1, x bar 2, and so on for my different samples. So I set up this thing I'm going to call xbar.boot, so it's my bootstrap averages. Try to give it a name that I can remember what it is. And so up here it appeared there's 1,000 values, 0 right now because it doesn't have anything in it. In R you can do little loops. Right? So this is a loop, called a for loop. It's going to go, there's going to be an index, little b there. It's going to start out as 1, and then 2, and then 3, and so on. And it's going to go for 1,000 times. And each time it happens, it's going to draw a sample, right? This is my bootstrap sample here, a sampling from my data x n times, 30 times with replacement. Right? So that gives me my x, I call it x star, my sample of data. Right? And then I'm going to take the average of that and save it as the b entry number b in that vector. Right? So if I run all that, that's it. It's pretty fast. And the first 5 values. Now I don't get exactly what I had before because I've done a few random number generations in between. It's kind of, but this is kind of the scale of the thing that you're talking about, right? The x bars. Right? My one sample had 6.03. Right? But with slight variations, I get these different ones. So if I sample these, one way to look at how things are changing. Let me sort my data x. Right? These are the x's in ascending order. One of these samples is going to be kind of like x, but a little bit different. So if I sort those, I'm sorting it so we can see the differences, otherwise it's so this one sample here, it picked 4 3 times. It looks like it picked 8 1 time instead of 2 times. And so there's a little bit of variability there. If we average the bootstrap sample, it's a little bit different than the other one. Right? But I've done it 1,000 times. The histogram of those things, bar, bootstrap, that's the histogram of these things. Bigger. Maybe we can make them, a few more breaks there. That's a little bit, maybe too many. Right? It didn't like that, huh? Why doesn't it be stuck on something? That looks a little nicer, a little smoother. So my x bars are kind of in that range for my replication, for the simulation. So the standard error really is describing how wide this distribution is of my x bars. So from 6 up to 6.5 is about 0.5. That's about 2 standard errors. So my standard error should be about 0.25, right? About a quarter. And so the standard deviation of those things, well, one time I did it with a quarter. It's a little bit less than this time. There's some variability to it, so. My confidence interval would be taking the mean minus 1.96 times the bootstrap standard error. There's no extra dividing by square root of it because it's a standard deviation of x bars. So that would give me, an interval 5.56 up to 6.5. And that would be a 95% confidence interval for the average EPGAR score for infants like these that are included in this group. So I didn't have to use S over the square root, but use simulation instead. So again, that the value of looking at that could be that it kind of illustrates what a sampling distribution is. Try to get at that, what the standard error, what is that really measuring? What does S over this, or sigma over the square root of A really pertain to? And secondly, in other cases, again, it's very hard to do mathematical formulas for very complicated estimators, where you might actually be going through a whole series of steps to do weighting and adjustment and things like that, data cleaning to data. So there might not be much of a mathematical formula that would capture it all. But Bootstrap, through simulation, might be able to capture more. So it's relevant. Right? So by comparison, if we went through the formula that we did at the beginning, right, there's the standard deviation of x is about 1.3. Again, the histogram with the x's, there's not many x's, right, but it's wider in any case, and it's skewed. So that's the histogram looking at that. Oops. So we did sigma over the square root of n. We use our sample data. S over the square root of n, about 2.42. Right, that's about what we were getting from the standard deviation of the x bars. And again, the histogram of those x bars, from the middle part here, going out 1, going out 2, standard errors, is about the central 95% or so that we would hope. Right. So that's the key parts of confidence intervals. So we have a confidence interval for a mean that we're going to take x bar plus or minus the z-value times the standard error. And if we use the formula, we're going to do sigma over the square root of n. Or we're going to do x bar plus or minus this z-value times this bootstrap standard error. And these two things should give you approximately the same answers. We should do different things. What we're going to do going forward is we're going to relax. Beginning, we know this, and that's going to force us to use something called a t-distribution here. We're going to do a different version for proportions, like a binomial one. But the big picture is going to be kind of an estimate plus or minus a value here times the standard error. Even though we're going to look at a lot of different confidence intervals for different applications, the general form and the general idea of what we're trying to do is going to remain the same. So if you understand this case, and then can see how it generalizes, then it won't seem like just I'm throwing a lot of formulas at you, although I might. Okay. All right, thank you.
I realized I forgot to attach them.
Oh, okay. Really? Bye, see you.
Thank you.
Thank you. Thanks.
Who were you, Professor?
Thank you. You too.